सो सबैजना सर म्यामहरूलाई नमस्ते। आई थिङ्क आइएम अडिबल टु यु। मैले बोलेको सुनिरहेको छ नि?
छ सर।
थ्याङ्क यू सो मच। सो मैले थोरै ब्याकग्राउन्ड भनिहालेँ। सो यो चाहिँ काठमाडौँ युनिभर्सिटी डिपार्टमेन्ट अफ स्टेम एडुकेसन र अलि बढी चाहिँ हाम्रो भद्रमान सरको रिक्वेस्टमा सो सो वी हेभ एक्चुली स्टार्टेड दिस सेसन्स होइन, यो म्याथमेटिक्समा पनि अलिकति त्यसको हिस्ट्री र त्यसको अदर एरियाजलाई कसरी हामी म्याथमेटिक्स स्कलरमध्येमा चाहिँ अलिक बढी कसरी पुर्याउन सकिन्छ, अनि जुन हिस्ट्री छ त्यसलाई चाहिँ कसरी प्रिजर्भ गर्न सकिन्छ भन्ने कुरामा चाहिँ यो सेसन हामीले सुरु गरेका थियौँ। सो टेक्निकली दिस इज आवर सेसन 6, किनकि हामीले 0 भन्ने सेसन पनि गरेका थियौँ। अनि बिफोर दसैँ चाहिँ अलिकति यो टेक्निकल इस्युजले गर्दाखेरि वी आर नट एबल टु एक्चुअली कन्डक्ट दिस सेसन होइन। अनि आज चाहिँ हामीले त्यो प्रमिस गरे अनुसार चाहिँ यो दसैँ तिहार र छठ पछाडि चाहिँ हामी सो वी विल रिज्युम आवर सेसन भनेर जुन प्रमिस गरेको थियो। सो बेस्ड अन द्याट प्रमिस हामीले चाहिँ आजको सेसन यो जुन होइन हिस्ट्री र त्यसको अदर एरियाज अफ म्याथमेटिक्समा जुन हामी सेसन वेबिनार सिरिजहरू गरिरहेछौँ त्यो चाहिँ आजबाट हामी कन्टिन्यू गर्छौँ। सो फर्स्टमा चाहिँ म सबै पार्टिसिपेन्ट सर म्यामहरूलाई सो थ्याङ्क यू सो मच फर जोइनिङ दिस एक्सलेन्ट सेसन भन्छु म चाहिँ, बिकज भद्रमान सर इज वान अफ द लेजेन्ड लिभिङ लेजेन्ड्स होइन, जसबाट चाहिँ हामीले एउटा लाइभ लेक्चर्सहरू चाहिँ जुन हिस्ट्रीसँग रिलेटेड अनि म्याथमेटिक्ससँग रिलेटेड चाहिँ लेक्चर्सहरू सुन्न पाइरहेछौँ। सो द्याट हामीले पनि अलिकति म्याथ्स एजुकेसनमा र म्याथमेटिक्समा अलिकति केही कन्ट्रिब्युसन गर्न सक्छौँ भन्ने एउटा इन्करेजमेन्ट जस्तो पनि लाग्छ मलाई, एउटा मोटिभेसन पनि जस्तो लाग्छ। सो विदाउट एनी डिले, सो आई kindly request Bhadra Man sir to start the session. Bhadra Man sir, over to you.
Okay, good evening everybody. यो चाहिँ नि अघि भनेको जस्तै लामो ब्रेक almost this S5 was scheduled for October 5 or October 4, but due to the NTR festival, so we moved to November 12. And today's topic, so the theme is mathematics through the ages. So the whole seminar, S0 was my life, mathematics my life. Now from S1 we had different topics under the mathematics through the ages. So what I wanted to do is show you how different disciplines of mathematics originated, giving some introduction of some important mathematicians and some places and some important, vitally important disciplines on a mathematical theme. So today's is a very simple one, which is familiar to almost all of us. So this theme is Fibonacci numbers and golden ratio, which is known to all of us, I hope so. But what I'll try to do is try to introduce or induce some of the elements which you may have not heard or seen in the previous during your study or whatever knowledge you gain. Because this Fibonacci numbers and golden ratio, you can go to YouTube, and there are a lot of different varieties of YouTube presentation regarding Fibonacci number and golden ratio. So it's not a unique one. Later on, some of my presentations will be unique, but this one is not unique. But to continue with the mathematics through the ages, I think this one also is important. That's why I'll start with my photo here from my garden. You can see this is my garden. I have stupa there, Buddha there, the bale here. You can see bale is also here, and wife is here. So my two twin granddaughters are there. Okay. I'm showing this because the next slide starts from the flower which is in my garden. So I have this flower in this garden, one flower. Everybody knows the Kane Botma Ubrincha. I don't know the botanical name because I am from the physical group. And You can see there are two petals. There are only two petals in this flower. Then I have this another flower. It is known to everybody. It has three petals. You can see over here, and the other flower from my garden, which has 5 petals, and I have another very simple white flower here, which has 8 petals. So what I try to do is so that mathematics is not an abstract subject. It has originated from the nature. We take it from nature, and we try to learn mathematics through the nature. So you can see, if you carefully look at our surrounding in the nature, you will see such very nice things, just like I have shown here 4 flowers here, 2 petals, 3 petals, 5 petals, 5 petals. And if you now convert it into our mathematics, then you see that 2 plus 3 will give us 5, and 3 plus 5 will just give 8. And these numbers are really Fibonacci numbers, about which we will talk later on. But I will start with a puzzle. So here is a picture of the bee starting at the end of some cells in hive. So the hive cells is like this. I have two nomenclature these hives in the ascending way: 1, 2, 3, 4, 5, 6, 7, 8. Even numbers are on the top, odd numbers are on the bottom. Now the problem is like this. So bee, it can start at either cell 1 or cell 2 as shown in the arrow, and moves only to the right. That is only the cell with a higher number in it. So this is how the cell behaves when entering into hives. The hive. This is logic. How it goes. You can start at cell 1 or cell 2. Because from here, there are 2 options here. So you can go to 2. From there, if you have gone to 2, you can come to 3 or 4 and so on. From 1, you can go to 2 or 3 and so on. So let's see how this bee will behave when the bee enters into this hive. So there's only one part to cell 1. Okay. There's only one part here.
Bhadra sir?
Other.
सरको त्यो माइक थोरै फिक्स गर्नु पर्ला, कस्तो नोइज आइरहेछ। अलि कस्तो डिस्टर्बिङ साउन्ड आइरहेछ। आइरहेछ तर थोरै नोइज चाहिँ आइरहेछ। इट्स ओके सर।
There's only one path to go to cell 1. There are 2 ways to go to cell 2. You can see either directly by cell 1, 2, or you can go directly to 2, or you can go through 1 and then 2. There are 2 ways to this cell 2, directly this one or by cell 1. For cell 3, you can see it can go through 1, 2, 3, it can go through 1 and 3, and it can go for 2 and 3. So that is, there are 3 different parts for the bee. The question is, how many parts are there from the start to cell number 10? Let us say. So this is the problem here. It's a puzzle. It's something like a puzzle. Now let's try to give the answer to this puzzle. The answer will give us a Fibonacci number. Strangely, it will give us a Fibonacci number. Numbers, as you know, if you know, the Fibonacci numbers are 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 1, 2, 33, and so on. They form what is known as the Fibonacci numbers or Fibonacci sequence. We also call Fibonacci sequence now. Once I write in this pattern, then it becomes mathematically a sequence. But the original problem was with the rabbit. The problem with the rabbit was, what does this have to do with the rabbit, this Fibonacci numbers? Really, the original problem was with the rabbit. It was from Liber Abaci, published in 1212 by Leonard Fibonacci. So that's why it is called, since he was the first to introduce this number with the example of this pair of rabbits. So it is we call it now the Fibonacci number. So it's a problem of 1202. It's a very old problem. So if a certain man puts a pair of rabbits in a place. This Leonardo Fibonacci was a monk in a certain monastery. A certain man put a pair of rabbits in a place surrounding on all sides by the wall. How many pairs of rabbits can be produced from that pair in a year? If it is supposed that every month each pair which is give birth a new pair, not only one, it gives birth to a pair. This from the second month become productive. The first month is dormant month, and only in the second month it will start giving productions. It will give the other pair of more rabbits. So in the first month we have only pair is the number of pairs. Number of pairs is only one. In the second month also it will be number one because it takes 1 month alternative to make a production. So in the third month only there will be a production of the another pair. So there will be 2 pairs. Now this is a new pair. This is a new pair. It will not give the production. Only this will give the production. So in the next month, the fourth month, it will have this one is as it is. This one will give a new digit like this one. So now we have 3 pairs now. Now in the 6th month, this one will not give any new production. Only these 2 will give production. So it becomes like this one. Okay, it is already there. Now the new production are like this. So this one also gives a new production. This one. Now we have 5. You can see on the right number of pairs is 1, 1, 2, 3, 5, and this is what is known as the Fibonacci numbers. From 1212 is for example given from the practical one because this monk in the monastery or actually raising rabbits in that premises inside the source, and he noticed this phenomena, and from this phenomena he wrote this mathematics, and then we got this Fibonacci. Actually it type was like 1, 1, 2, 3, 5, it will go on right now and so on. So this is the original version of Fibonacci numbers which all of us I hope know about it. So this is Fibonacci number. Fibonacci number is normally noted by a recurring formula like this: Fn plus 1. Next Fibonacci number will be the sum of the previous 2 numbers. Okay. If you want to write here, it will be sum of this 24 and 237 will give us 377. With the next so Fibonacci is what you can find. Next Fibonacci number you can find with the help of recurring. But with a mathematician, when we have a sequence, we like to find a formula to find value of the nth Fibonacci number of the sequence. So it is given by definition. It's very easily seen that Fibonacci number as adding the previous 2 numbers. So this is the recurring formula. But as I have said, we should not be satisfied with the recurring formula. We should be able to generate the general formula to find general term. But to make it complete Fibonacci number, so it correlate with 1, 1, 2, 3, and so on. But to make it a mathematically and make a complete one, to add one term, f0 is equal to 0. It's not there. And f1 is of course 1. Just like my seminar series, I started with S0 and we have this one, this 2. So in case of this Fibonacci number also, we add this F0 is equal to 0 and then continue with F1 and so on. Also, this is the real Fibonacci number, which is not generally shown in mathematical books. They start with 1, 1 and so on. And 0 has no significance. 0 plus 1 is equal to 1. So we don't generally write 0. But to make it complete, you should add this f0 which is equal to 0. Now, if you find the ratio of these Fibonacci numbers 1 by 1, you get 1, 1 by 2, 2 by 1, 2, and 3 by 2, 5, and so on. Let's find the ratio of the two Fibonacci proceeding corresponding to Fibonacci numbers. So if you go on finding the ratio, still you can see that after this one you can see 1.6, and then from here 1.61. The recurring is here 1.617 now. After that we have 1.618. Then now here you can see it's a bit strange. This is 179, not totally 8. Then after this you will see all the line coming will be 1.6180. The question is, then what is the ratio of Fn plus 1 Fn when n tends to infinity? So if you find this ratio, as you can see now, it is being stable at 6.180 and 3 here, and so it will continue like this. And this ratio is very interesting. Generally, it is represented by this first USA card, Visa card, and this Visa card was made to illustrate this Fn plus 1 ratio of Fn plus Fn, about which we will talk later on also. So this, whatever we have, is known as the golden ratio. Today's talk is on Fibonacci numbers and golden ratio. That is why I have shown this one. Though we don't know the value of golden ratio at this time, but we can see that it will be 1.61, and so on. But it is very interesting that this ratio of this Visa card horizontally and vertically actually gives us a golden ratio. If you have seen, not our Nepali card, Visa card, but the American Visa card, which is very standard one, will give us a golden ratio. Now, many things will be very clear when we have a graph. So if you look at this number, the number here 1, 2, 3, 4, 8, 1, these are Fibonacci numbers. And if you find the ratio of Fibonacci number, Fn plus 1 over Fn, start with 2, 2 by 1, 2, and so slowly it moves like this, and it will go horizontally like this at 1.6, and a bit above 1.6 is 1.618033, and so on. And this limit will give us what is known as the golden ratio. We have not actually found the value of golden ratio. We have found the approximate of golden ratio. Now this golden ratio, as I said, all our mathematics are generated from nature. Now if you look at Homo sapiens, that is people like us, okay, statistical result shows that the height of a human body to length from the head to hip is a golden ratio. So if it is a Homo sapien like this man, then this is the total height of the human body. And we look at the length from head to the hip. Here hip is by small h. Then we find that this S capital S by small h, this capital S by small h, only divided by 3 is what is known as the golden ratio. And for normal people, it average like this one. For male, it is 13 by 8. And for female, it's 8 by 5. So, ratio of male is more closer to golden ratio than of the females. We know that most of the females are a bit dwarf compared to male. And when the first child is born, at the birth, generally the ratio is 2:1, the first one. So this is how golden ratio and Fibonacci number is related with our human body. Now one more problem, which I call a staircase problem. A staircase has n steps. Okay, what would be the n? You can walk up taking 1 or 2 at a time. But generally, you see, we normal people, just like me, I take only 2 steps. My granddaughters, they like to take 2 steps at a time. Of course, they can't climb 3 steps, So generally, people walk one step at a time or two steps at a time. Then the question is, how many ways can you go up to n step? Let's put it in a tabular form. The mathematicians also like look at from in a tabular form. So number of steps. To have only one step, just like small step, then you can. There's no only one way of going up. If there are two steps, staircase of two steps, then you can go in two ways. How you can go two ways? You can go one at a time, or you can make a jump of two steps. So there are two ways. So three, then I say that you can go by three ways, like this one. Go 1, 1, or 1, or you can 1 plus 2, or you can start with 2 and then go to 1. You will arrive at the first step, and so on. And so on, you can see that at 4 it will be 5, and for n, whatever it may be, it is Gn. Now, you see, this is not really a Fibonacci number, but I'll call it Gn. Looks like Fibonacci number. 1, 2, 3, 5, and of course, the next one will be 8. Or number of steps 5, you will have the value 8. You can go and calculate this simple one. 5 is 8. So I'll call this as Gn. Now, then the question is, how do you relate this Gn with Fn, Fibonacci numbers? So, this staircase again step, you walk off taking 1 or 2 at a time. How many is it like this? For 1, 1, for 2, 2, for 3, 3, for 4, and I call it Gn. So this Gn plus 1 also is a recurring formula, Gn plus Gn minus 1, preceding two forms. Now, Fibonacci number, I will put the Fibonacci number down so that we can compare it. It's like this one. Now, can you see some similarity and then try to find the relation between this Gn and Fn? So mathematicians always try to look at such problems, making link between different type of problems. So are successful making link between such type of problem, then you are a good mathematician, I would say like that. So it looks that Gn is for Fn. No, it's not totally Fn, as we have seen that. We go back. It's totally, the table are not identical, but they look similar. Okay. Now if you look carefully over here, I have 1, 2, 3, 5 here. I have 1, 2, 3, 5 starting from here. Okay, this 1, 2, 3, 5 starts from here. So there should be a link like this. So it is not totally, Gn is not identical to Fn, but Gn will be Fn plus 1. So move by one step over here. You can see that. Start from one step right side. So then we have made a link between this Gn, the step problem, and the rabbit problem or beehive problem, which gives us Fibonacci number Fn. Let's look at the first n Fibonacci numbers and find its sum. I put F0 is equal to 0, so I have 0 here, and so on. So this is sum of here. So 0, 1, 2, 3, 4, 7, 12, 20, 28. It does not make too much sense, but if I add 1 to all these numbers, if I add 1 to all these two numbers, then you can see it will give us 1, 2, 3, 5, 8, 13, 8, 1, 20. So it gives a Fibonacci. So if you add the sum of Fibonacci numbers and add 1 again, then you will arrive at another Fibonacci number. You will again come back to Fibonacci number. So there is a relation between the sum of Fibonacci numbers, okay, and the real Fibonacci numbers. What you have to do is you have to add 1 to each of them. And you will strangely see that these Fibonacci numbers are here. 3 is here, 5 is from here, 8 is here, and 13 is here. But so they move like this one. So that means there should be a formula to relate the sum of Fibonacci numbers with the Fibonacci numbers. So that means Fibonacci numbers, if you relate it, it will be this number which is reduced by -1. Okay. So sum of this Fibonacci number is If it is number n plus 2, because it is not here, it is above 2, so n plus 2, and you take out 1. So this is how we should learn mathematics and teach mathematics. Further, so this general formula, you can find general formula, but it is very clumsy. Fm will be 1 by root 5, 1 plus root 5 by 2 to the power n, minus 1 by root 5 to the power n. So the general formula to find Fibonacci number is very nasty, very clumsy like this. But there is one small history behind this number 1 plus root 5 by 2. Because I am a graduate from Russia. So when the Russian, of course, of other countries, European countries, also made this steam engine, so they made a steam engine and had certain power. Steam engine could drive with certain power. Then the scientist or the engineer who made the steam engine and his boss said that I want a steam engine with the double power which we have right now. And so it took the help of the mathematicians, whatever it is, his friends and so on, colleagues. So what they found is if you multiply the size or the diameter of this steam boiler, it should be multiplied by this number 1 plus 5 by 2, so that you will get double power. So there's a history about making this steam engine also. But anyway, the general formula for Fibonacci number is very clumsy. It looks like Fn is equal to 1 by root 5 and 1 plus root 5 to the power n minus root 5. So let us now try to find this, how we find this general formula. Okay. So as a mathematician, it will be a task to find this clumsy formula which gives the general value of Fibonacci number. Over here, these two quantities are the roots of the equation. You can easily see that this quantity, 1 plus root 5 by 2, 1 minus root 5 by 2, are very simple. They are the roots of a very simple quadratic equation, x squared minus x minus 1. So we should find the roots of this very simple quadratic equation, x squared minus x minus 1 is equal to 0. Then you will have the value 1 plus root 5 by 2 and 1 minus root 5 by 2. 1 plus minus root 5 by 2, and this is and so very simple one. You can use the quadratic formula, and then you will have this two numbers. Now, this simple looking quadratic equation, x squared minus x minus 1, is also very interesting. This is a very interesting quadratic number which you come across in mathematics in many places. This equation is obtained in several problems. Some of those problems are given in the following slides. If you come later on, in the following slides, I show which type of problems will give rise to this simple quadratic equation, x squared minus x minus 1. Right now, I will come back to Fibonacci numbers. There are two very important properties of Fibonacci number. One, which we have already seen, that the sum of the Fibonacci numbers of n is equal to Fn plus 2 minus 1, which we have illustrated with the example itself. Now, there's other important property of Fibonacci numbers, sum of the Fibonacci numbers. This was the sum of the Fibonacci numbers. This is the sum of the Fibonacci squares. The sum of the squares of Fibonacci number will give us Fn into Fn plus 1. Sum will of the squares will is converting into something like a rectangle, because if you find the product of two values, you will have a rectangle. Okay. Now let me illustrate it with the help of geometrical sequence. So Fibonacci number have start from 1 1. So I'll take squares with side 1. Okay. So I have taken the first two Fibonacci numbers 1 1 and put it side by side. That means I am taking the sum of 1 square and 1 square, and you will get this rectangle. It's a rectangle. Wait, this is 1 and it is 2. Now I can add to it F3. F3 is 2 square. The 1 F1 is 1, F2 is 1, F3 is 2, 2 square. Now I have found a rectangle. It's a rectangle with 2 into 3. Okay. Now the fourth one will equal 3. The next Fibonacci number 3. I'll put the rectangle with 3. 3 square means rectangle, square with 3. I'll add here square 3. Now it is again a rectangle with 3 into 5. And so on. You go on adding that. Okay. You can see now this is geometrical explanation of f1 square plus f2 square plus f3 square and so on is equal to fn plus f3. Okay, so sum of the squares of Fibonacci numbers will be fn into fn plus 1, which will turn into a rectangle. Because when you are teaching and illustrating, you can have some mathematical explanation, or very illustrative will be geometrical representation. Now, Binet's formula. I don't know how many of you have heard about this Binet formula. There's a lemma for this to find this formula. If x square is equal to x plus 1, actually this is the same quadratic equation, x square minus x minus 1. I have written as x square is equal to x plus 1. Then for n is equal to 2, 2, 3, 4. Then I can write x to the power n will be fn, that Fibonacci number, n, x plus x. The f Fibonacci m minus n minus 1. You can easily find that. And you see that this is x squared minus x minus 1, which we already have said that we have two roots, 1 plus alpha 5 plus 1 plus root 5 by 2. Another root beta 1. Thus for all n is equal to 2, 3, 4, for n is equal to 1, we have alpha n will be fn, putting the value over here. Since alpha and beta are its roots, then roots must satisfy the given equation. So here also I put alpha n is equal to fn alpha plus fn minus 1. And for beta, you'll have beta to power n, fn, here beta and fn minus 1. Now if you find the difference of this alpha n and beta n, you'll have fn alpha minus beta. So alpha n, beta n will be, if you can take fn common, this fn minus 1, fn cancel, we'll have fn common, alpha minus beta. Here we have a simple form, alpha n minus beta n will be like this. Now, alpha n minus beta will be fn times alpha minus beta. Noting that alpha minus beta is equal to 5. If you now sum of this alpha and beta, you know that alpha is here, beta here. If you sum up, then 1 by root 5 by 2, 1 by root 5 will cancel, you will have half, and half will be here, and then you will have root 5, only here. Okay. So now if you put alpha minus beta, value of alpha minus beta here, fn we know that, and then we'll have the value of fn, we have to find the value. It will be this formula, and this is known as the Binet formula. So the general formula, find the general term of a Fibonacci number is given by what is known as Binet's formula. Looking from the 1 by root 5, 1 plus root 5 by 2, power n minus 1 by root 5 by 2 power n. So we have deduced the general term formula for the Fibonacci numbers. Let's go forward. So when you are a mathematician, when we have something, you always try to generalize it so that we have new ideas and new type of mathematics. Fibonacci sequence can be generalized in two ways: by preserving the recurrence relation and altering the first two terms. So, recurring operator means fn plus 1 is equal to fn minus fn minus 1. And you just change the first two terms. In the Fibonacci numbers, it was 1, 1. Now, if you turn into some other starting two numbers, then you will have another type of interesting sequences. So, one way. Another way is by preserving the first two numbers, that's 1, 1, 1, sequence, but altering the recurrence relation slightly. Instead of n minus n plus 1 is equal to fn minus fn minus 1, you can just slightly change it. So you'll have another type of sequence. So let's look at example of this generalized Fibonacci sequences. Preserving the recurrence relation and altering the first two terms. So instead of 1, 1, I write PQ. Okay, then 6 will be another term will be sum of the previous two, previous Q. The next one will be P plus twice Q. You have to add these two. The next one will be have to add these two, 2P plus 3Q, and so on. So Gn will be, of course, Gn minus 1 plus Gn minus 2. So Gn greater than 2. So this is one way of generalizing. And for physical 1, physical 1, of course, we come back to Fibonacci number. So we have seen 1, 1, 5, 2, 3, 5, 8. Now, second way is changing the first two terms. For example, first 2 is equal to 1, first term is 2, then 1. Then you go on writing 2 plus 1 is 3, 3 plus 1 is 4, 3 plus 4 is 7, and 4 7 is 11, and so on. Now, this one, 2, 1, 3, 4, 7 sequence is denoted by L1, L2, L3, L4, L5, and it has a very nice terminology for this sequence. It is called the Lucas sequence. So it's also very interesting and applicable sequence, about which I will not talk too much, but it's a generalized Fibonacci number. Lucas sequence is a generalized Fibonacci number where the first two terms start from 2 and 1 and then go on with the sequence just like the Fibonacci number. So Lucas numbers are 2, 1, 3, 4, 7, 11, 18. And just like in the previous case, I'll define L0 as 2. So Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13, 20, and so on. Then you can find the relation again between the Fibonacci numbers and the Lucas, this new sequence Lucas, Ln. It will be Fn minus 1 plus Fn plus 1. So it's a, two terms are different here. You can see it's the sum of the difference of two terms. Fn minus 1 plus Fn plus 1. So you can see that, 2 and 1 will give us 3. Okay. I plus 2 will give us 7. Okay. And so on. So you can see it's a jump of two terms. Okay. 3 and 8, 11. 5 and 13, 18. So that is the relation between Lucas number and Fibonacci numbers. And we can also find Binet's formula, similar Binet's formula for the Lucas numbers. So it's very simple. Lucas number is found because it's a difference over here. It's a small arithmetic. Lucas number will have Ln plus Bn. You know Ln is 1 plus root 5 by 2. Bn is 1 minus root 5 by 2. Okay. Now going back to problems. Now let's talk about sequence. We'll come back to Fibonacci numbers again. But let's now talk a bit about golden ratio. There was a problem or a quiz showing this pattern to the general people and asking which one do you like best, which one do you like the least. Different. You see, it's a very nice square, and there are other rectangles over here of different sizes. So I'll give the sizes later on. Then, for giving the sizes, you ask the general people and try to find your opinion, which one do you like the best among these 10 ones, and which one do you like the least. And so then you have to make statistical analysis with a survey from a group of people. So the answer to that survey I'll give later on. Now let me give the history of the golden ratio, which is I know known to you. The straight line is said to have been caught in extreme and mean ratio, when as the whole line is to the greater segment, so is the greater to the less one. That means have line AB. I'll cut it as C. Okay, with the notation that this CB, the smaller one, has 1, and the bigger one, which we don't know, is X. 1 plus something, we don't know. But the CB is 1. Bigger one means X should be greater than. If you go to textbook, they don't always show like that. They say A, B, and A plus B, they will show like this. Instead of A plus B, I am writing X and 1. So the ratio of AC to CB is equal to ratio of AB to CB. What definitions mean? That means X by 1 is equal to whole 1. This is X plus 1 by the bigger one, X. Okay. Bigger one by smaller one, the bigger one by smaller one. Now, general cross multiplication will give 1 times X plus 1 equal to X into X square. And this will give us the formula X square minus X. And comparing with our quadratic equation, then we have X equal to minus B plus minus 1. Put the value over here. It will have X equal to plus minus. So you can see this is what we had in our Binet formula, that is general value of form of Fibonacci numbers, and we are having from this golden ratio. So this means Fibonacci number and golden ratio has a close link, which also has been shown by finding the ratio of the Fibonacci numbers. And this X will be taking positive number. It will be 1 plus root 5 by 2, which is 1.6. So that this is what you have. And if you take minus value, since root 5 will be greater than 1, it will be a minus value. It will be same number with minus. Okay, minus sign. Now, from the very school arithmetic, we have seen this continued fraction. 1 plus 1 by 1 by 1 by 2 by 1 plus 1. So this is known as continued fraction. This continued fraction is generally denoted by phi. So we have this phi is equal to 1 plus this whole is phi. If I do not hold this whole as phi, this is also phi because it's infinite series. So then I have phi is equal to 1 plus 1 by phi. Now if I cross multiply this, phi is equal to 1 plus 1 by phi. It is again a quadratic equation, and this phi will give us the same value. Phi is equal to 1 plus 1 by 2. So actually, this is what is known as the golden ratio phi, denoted by capital I, 1 plus 1. So I have now shown that golden ratio, value of golden ratio comes in many forms over here. Sequence of continued fractions. That was one continued fraction. Now I'll give a sequence of continued fractions. 1 plus 1 by 1, 1 plus 1 by 1 plus. This is a sequence of continued. Such a sequence we'll call sequence of continued fractions. Now, if I try to find the general recurrent equation for it, then you get this Fn plus 1. This Fn plus 1 will be only 1 plus this, 1 plus 1 plus. So the recurrent formula Fn, Xn plus 1 is 1 upon 1 plus Xn. Now, if you find the value of Xn1, if you say that if this sequence has a limit A, then it should be A equal to 1 plus 1 by A. So it also again gives the same quadratic formula, A square minus A is equal to 1, and the value of A will be 1 plus 1. So in another instance also, we have the same golden ratio. One more approach. The quantity F is also defined as root over 1 plus under root 1 plus 1 under root. This is again a sequence, something like a sequence. Continued under roots. In this case, we have phi is equal to root over 1 plus 5. If you square it, then we have phi square equal to 1 plus 5, which is f square 5. We again gave the same golden ratio. You can see, you see golden ratio in many formats in mathematics. many forms. Now let's try to make a comparison between relation between Fibonacci numbers and the geometrical sequence. Fibonacci number we have now not learned so much. The geometrical sequence we know from school mathematics. So let Gn will C into Qn be a geometric progression. Let C and Q is not equal to 0. Then Gn plus 1 is Gn plus Gn minus 1. It is looking very similar to Fibonacci number. And what is Gn? Gn is CQ. And so this will be, if you put a value of C here, C times Q n plus 1, put a value of Gn here, C into Q plus 1, which is 1. Okay, and so यो यहाँ राख्नुपर्ने मैले यो n चाहिँ यहाँ तल गएछ राख्नु है and C you can take out, then you have Qn plus 1 is equal to Qn plus Qn minus 1, and from here if you put value n is equal to 1, then you have Q square is equal to Q plus 1. Put the value n is equal to 0, n is equal to 0, n is equal to 0, it will give us n is equal to 1, और यहाँ चाहिँ उसको q to the power 1, so 1 and 0, q to the power 0 is equal to 1. So we have, again we have the same quadratic equation, x squared is equal to q minus 1. And two roots are again the same one. So that means there is a direct relation between Fibonacci number and geometrical sequence. So geometrical sequence is C times 1 plus root 5 by 2 to the power n. And our value of Gn will be C times 1 minus root 5 to the power n. And so Fibonacci number is general Gn minus G prime by n. That is for negative values, where C, if you take the value of 1 by root 5, then it will be the natural number will turn into Fibonacci number. That's a sequence. Now we have, in mathematics, we have another number called Fibonacci coefficient, binomial coefficient. There should be a relation between these coefficients. Let's look at the Pascal Fibonacci binomial coefficient, which is also known as Pascal triangle. When Pascal first wrote the Pascal triangle, so are not in a triangle, so are in this rectangular triangle, like as I have shown. Look at the history book on Pascal. Then in the initial page, it wrote, Pascal wrote the triangle in this rectangle. Later on, we put it in a this equilateral triangle. You look at this and then try to find the sum of the elements in this Pascal, that is coefficients in this Pascal triangle. You see that if I make it a slanting one here, so 1 is already here, so this will give us 1, this will give us 1 plus 1 will give us 2, 1 plus 2 will give us 3, 1, 3, 5 is 4. So you can see again we are having, from this binomial coefficient, we are again having the Fibonacci number. So that means there is a direct connection between Fibonacci number and the binomial coefficients. And of course, you know, Fn then can be written in terms of this binomial coefficients. I am writing in terms of like this. So you can also write Fibonacci number in terms of binomial coefficients. Now, this is one borrowed part of the slide given by J.F.O. Cornell. So I have created over here, link over here, go to here. J.F.O. Cornell. So he talks about the Coulomb ratio. I have put it here so that you can also then look at this link. This is his slides. I am just showing to you Coulomb ratio, what is it? Coulomb ratio in art and architecture, Coulomb ratio in nature, and so on. The first written appearance in the book Elements by Euclid came written around 3000 BC. There are 13 volumes on geometry and number theory on this Elements by Euclid, which we will comment on also. We have and remain unaltered for 2000 years. This book, Elements by Euclid. Abraham Lincoln studied elements for training in reasoning and demonstrating, that is for logic. It's a best-selling book in the history of mathematics. Only the Bible outstood elements until the 20th century. Of course, after 20th century, the pilot has gone down and mathematics is coming up. So, we have already seen that the straight line is said to have been extreme and mean ratio when it has a whole number. So, here he writes the same one which I have taken. In this slide also, he has put the same value over here, just like the partial sum for this other roots. Root 1 will be 1, root 1 plus root 2. And so on. You can see slowly this partial sums goes to 1.68. Now you should say, know that if you have sequence and the partial sums go to a certain number, and that will be the limit as it has been studied in our mathematics. That's how it gives us golden ratio to 3. So this is also the same over here. I am showing here with the help of partial sum. Now, this one I have already shown, but I have put it in inverted one. He has put it in 1, 1, then add 1, and add 3, add 4, add 5, add 6, add 7, 8. Now, if you put a radius on this side, for example, here I have 1, 1, so I put a radius here. When I have 2, I put a radius here. When I have 4, I put a radius here, and so on. So when I have put a radius here, it turns into a spiral. So sometimes known as Archimedes spiral. And in some books, it is also known as God sign. This is known as God sign. And that is from the golden ratio. So this is from the golden ratio. Okay. 1, 1, 2, 2, 1 is here. 2, 3, 5, 8, 13. Which the Fibonacci numbers. That is, we have said that sum of squares of Fibonacci number is like this one. It gives a rectangle. Now going into nature, so this is what is known as sunflower. This Mona Lisa drawing is also related with Leonardo da Vinci. When they drew it, he has used the golden ratio for that. Golden ratio is like this. Of golden ratio. I am very fortunate to see this portrait of Mona Lisa in the Louvre Museum in France back in 1971. It's another one by see. It's a new structure that we have had, and there was a small advertisement. It also has a golden ratio. You can see the ratio is pentagon. And everywhere this use the above golden rectangle and spiral focuses point at a template for design layout, just like all these figures I have shown. You can also rotate, reflect. Some of them have reflected and rotated, and scale proportionally to maintain this ideal layout. You can also copy and paste into Photoshop, and you can do on your one whatever you like. Now, this Egyptian pyramid by 2600 BC and 1800 BC. They are constructed a lot of different pyramids in Egypt, and here also they have the golden ratio here. Now this is Platinum in Greece, built 705 BC. Here also that it is a golden ratio. And golden ratio, of course. I am very fortunate to have a photo in front of this building, Platinum in Greece. Okay, this is myself, photo taken on 31st July 1971 in front of Platinum, Greece. I was in Greece in 1971, you can see. I look like that in that age, 1971. United Nations building in New York is also constructed with the help of this rectangle, which is following the Fulton ratio of Fibonacci pattern. And I have shown that this first USA visa card was also made in shape of the golden ratio rectangle. There are a lot of buildings. This is very France. I have not seen this. France, Paris. Is also these are also in golden ratio. And in nature there are a lot of, as I have shown this one, these petals, even the growth of plants takes place according to golden ratio or according to Fibonacci. Cycles over here, they also follow the golden ratio numbers. Here I will show sunflower over here. You see there are 34 spirals here. And when if you go to the outer circle, it will have 55 spirals. So they are 34. And the spirals are in golden ratio numbers, Fibonacci numbers. Gustav Theodor Fischer, 1801-1887, published a book called Virtual Their Aesthetic Introduction to Aesthetic in 1876. Subjects were shown 10 rectangles in 1876. Subjects were shown 10 rectangles and asked which they found the most pleasing, and this pleasing which I have shown earlier. And so this is in 1876. This Gustav Theodor Fischer, he is actually a religious person. And so, which one do you like the best? Which one do you like the least? So, in the previous, I didn't put the ratio here. So, it is a square 1, 1, 5, 6, 4, 5, 3, 4, 7, 10, 2, 3, 5, 8, 10, 3, 1, 2, and so on, this ratio. And people were asked which you like the best, which you do not like the best. So, he made a statistical analysis and put it in a graph form, and he got the graph like this one. And they found that majority of them said that 5-8 ratio is the best one. And so 5-8, you can see, it is only the ratio of Fibonacci numbers. Oh, this is also Fibonacci numbers. Yes, are not. Okay. And when you put it in form, you see that most preference were 35% say that it is a golden ratio, that is 5/8, is the most preferred rectangle among these 10 rectangles. Later on, after almost a century, in 1908, the experiment was repeated with a more scientific manner. And now statistics were more stronger by C. Lau, and he got this result. So this is the result of Fischer in 1900, the later one now, and found that this is the best one. Ratio. Both the cases, they have same value. The golden ratio rectangle was the best one, preferred one. And in this preferred one, you can see are here. This one, 1-1 is not preferred. 2-5 is not preferred. 5-8 is the best one. And 2-3 is okay. And you can see it's also okay. Others are just like our postcards. They are another 3-4. They are not so nice compared to golden ratio. So this has been mathematically established that golden ratio is the nice. All these 10 figures I have shown. Now, since it's a topic which is familiar to you, as I've said, you can go to YouTube, and there are a lot of YouTubes on mass numbers and golden ratio. So I will stop over here for today because we have come back from festival mood. We don't like to sit too longer at this time. And then for you, I have given a food for thought. So I have talked with golden ratio. Then go home. First we are at home. Then try to find answer for this one. If there is a golden, there should be a silver ratio also. Have you ever heard about the silver ratio? I am not joking. In mathematics, there is also a silver ratio. So try to find for yourself what is silver ratio. Okay. And lastly, so this is food for thought. Now I have, believe it or not, problem for you also. Because also it is a food for thought. So I take a rectangle from the chessboard, 18 to 8. Okay, chessboard has 18 to 8. Then I divide it into 4 pieces like this one. Okay, the upper one, 3 into 5 rectangle. I have got to put a diagonal here. And I have a triangle with base, let's say, height and height 3. It's like that, the same one. Then I have this one diagonally put over there. Here it is, that is the 3, 5, and 3, 5 is there. So now I rearrange it. One I will take here. It is over here. This one is 1. Add that, I add 3 here. Then it becomes a big triangle. Then I take this 2 triangle, which is triangle here. The remaining is covered by this 4. Now I have this rectangle, converting a square with side 8 and 8, which will give us area 64. Now I have converted, pasted into a rectangle, which side 1, 2, 3, 4, 5, and 1, 2, 3, 4, 13. Then my area becomes 13 into 5 is 65. Now, by miracle, converting a square into a rectangle, 1 unit of area has been increased by miracle. But not by miracle, we are mathematicians, we should give a mathematical solution to this one. So I am putting as a question mark. Believe it or not, if you convert this 8 into 8 square into a 13 into 5, you can easily do that. You can take a cardboard or a graph board and then cut it and paste it. It will be exactly pasted as shown here, but the area will be increased by 1 unit. So then it is also a food for thought, and see why this 1 unit of area has increased. What is the mathematical reason behind that? Of course, you can go to internet and also find a not a simple solution, yes solution I was. So that will be enough for today, because we are back from the Sai Festival and TR. So next seminar will be in November 19th, which will be a bit longer. That will not be an easier topic, just like Fibonacci and golden ratio, which is well known to us. It is 6th seminar among the 15 remaining. Under the chain mathematics, and the topic will be abracadabra and Bernoulli family. Till next time on November 19th, and 1 week we'll meet again, talk about abracadabra and then Bernoulli family. Okay, thank you very much. So after some time, I'll send this PDF file and convert it. Thank you very much. Okay. Do you have any question on what I have here?
Okay. Thank you so much, Bhadra Man sir. So it was, quite interesting sessions. So I really enjoyed. So I would like to request our participants to, raise your questions if you have any questions to ask with Bhadra Man sir.
Because we have some time.
Yeah. सर म्यामहरूसँग केही क्वेसन छ आजको जुन कन्टेन्टमा होइन, अनि अब योभन्दा पछाडि हुने सेसन्सहरूको केही क्वेसन्सहरू छ भने, कन्फ्युजनहरू छ भने राख्न सक्नुहुन्छ।
सबैलाई थाकै ल्याएछ, फेसबुक मुटु अझै पनि बाँकी छ भनिरहेछ। थ्याङ्क यू। हामीले के बुझ्नुपर्छ भने, इफ यु क्यान रिलेट डिफ्रेन्ट एस्पेक्ट्स अफ म्याथमेटिक्स, then you are a real mathematician. टेक्स्टबुकमा भएको माथि पढेर त्यो पढ्यो त्यो पढ्यो भन्दाखेरि डिफ्रेन्ट टपिक्सहरूलाई कहाँ कहाँ ल्याएर रिलेट गर्नु सक्यो भने देन यु आर ए रियल म्याथमेटिक्स। त्यही गर्छन् साँच्चैको म्याथमेटिक्स। मैले अहिले प्रेजेन्टेसनमा गोल्डन रेसियो र फिबोनाची नम्बर थाहा नभएको भने त्यहाँभित्र टाकाटुकु कस्तो कस्तो सिक्वेन्स देखायो होइन, अरूले पनि गरेको छ। त्यस्तै गर्नु सक्यो भने देन यु हेभ अ रियल म्याथमेटिक्स। बिचबिचमा म चाहिँ जस्तै कहाँको कहाँ चाहिँ कुरो कनेक्ट गर्ने भन्ने चाहिँ
धनकुमारी म्याम, म्यामको केही थियो?
यस
ओके,
के छ
मलाई एकदमै इन्ट्रेस्टिङ लागेर एउटा क्वेसन
ल,
मात्रै जिज्ञासा मात्रै हो सर मेरो।
प्लिज राख्नुहोस्
म
न।
त्यति थाहा नभए यो सरले जुन धेरै टपिक्सहरूलाई इन्टर रिलेट गरेर प्रेजेन्ट गर्नुभएको थियो, रियल्ली इन्ट्रेस्टिङ। मैले जान्न खोजेको कि सर यो लुकास नम्बर अनि फिबोनाची नम्बरलाई सरले जुन लुकास सिक्वेन्स र जियोमेट्रिक सिक्वेन्ससँग रिलेट गर्नुभएको थियो नि, त्यसको त्यो कुनै एउटा ओपन प्रब्लम्सहरू पनि रेज गरेर सरले इन्ट्रोड्युस भनेको मतलब त्यहाँ छोडिदिनु भएको भए अझ रिसर्च गर्नेहरूलाई चाहिँ त्यो हुन्थ्यो कि जस्तो लाग्यो। एकदमै इन्ट्रेस्टिङ लाग्यो कि सर मलाई यो भएर। हाम्रो त्यो लुकास नम्बर, लुकास सिक्वेन्स अनि फिबोनाची नम्बर अनि जियोमेट्रिक सिक्वेन्ससँग जुन सरले रिलेट गर्नुभएको थियो नि, त्यसको चाहिँ जियोमेट्रिक सिक्वेन्स र लुकास सिक्वेन्सको इन्टर रिलेट पनि गर्न सकिन्छ कि भन्ने पनि थियो कि जस्तो लाग्यो।
एकदम सकिन्छ, त्यो सजिलो पनि छ, धेरै गाह्रो पनि छैन।
हजुर, त्यति मात्रै हो सर मेरो जिज्ञासा। थ्याङ्क
त्यो
यू
गर्न
सर।
सकिन्छ। र त्यो जुन अब धनले भनेपछि अरू जुन पार्टिसिपेन्टहरू छ जस्तो सुनिरहेको छ उहाँहरूले चाहिँ पनि अब आफूले ट्राई गरेर हेर्ने, त्यो गाह्रो छैन।
एकदम इन्ट्रेस्टिङ थियो कि सर, त्यही भएर मलाई त्यो क्वेसन मैले पढेको त छैन, त्यो क्वेसन एकदम मनमा आइहालेर जिज्ञासा लागेर सोधेको।
आफैमा इन्ट्रेस्टिङ थियो।
हजुर,
जस्तै चाहिँ फिबोनाची नम्बर यो कारणबाट आयो भनेको जस्तै लुकास कहाँबाट आयो भने फेरि त्यो हिस्ट्री हेर्न सकिन्छ।
फेरि त्यसरी पनि सर्च गर्न सकिने हो कि जस्तो लाग्यो।
उसको एप्लिकेसन पनि धेरै छ। अब यो कम्प्युटर म्याथको कम्प्युटर चाहिँ एप्लिकेसनमा त्यो त्यसको चाहिँ अलिकति त्यहाँ त्यसले चाहिँ भनिरहेको हुन्छ। त्यसरी कम्प्युटर एप्लिकेसनमा काम छ कि त्यसको।
हजुर, थ्याङ्क यू सर।
अनि अस्ति त्यो हिस्ट्रीको त्यो के भयो, मैले एउटा लिङ्क पठाइदिएको थिएँ।
त्यो यस्तो भयो सर, मैले टाइम एउटा चाहिँ जोइन गरेँ, त्यो 3:15 AM मा रहेछ। एकदम टाइम सेड्युल नै मिलेन सर, गाह्रो भयो। मैले नेक्स्ट चाहिँ जोइन गरिनँ सर, एउटा चाहिँ जोइन गरेँ मैले। त्यो जिनेट सिकालीको चाहिँ जोइन गरेँ मैले, त्यो लिडरसिप वाला। अर्को चाहिँ गर्न सकिनँ सर। थ्याङ्क यू सर फर लिङ्क। एकदम टाइम चाहिँ मिल्दो रहेन सर, हाम्रो EST र NPT मिल्दो रहेछ। हजुर,
मलाई पनि धेरै रिक्वेस्ट गरिरहेको छ, टाइमै मिलेन, कहाँ राति नछुटिकन हेरिराख्ने
हो सर। त्यो टाइम नमिलेर, टाइम जोन नमिलेर गाह्रो भएछ त्यसलाई।
ओके,
अरू साथीलाई पनि यो मेरो अर्को झन् इन्ट्रेस्टिङ छ। आब्राकाडाब्रा पनि इन्ट्रेस्टिङ छ। आब्राकाडाब्रा कसो यो चाहिँ फ्यामिलीको त झन् इन्ट्रेस्टिङ छ। अरूलाई साथीहरूलाई पनि जोइन गर्ने रिक्वेस्ट गरेको हुन्छ।
साथीहरूले ओनिङ्स ग्रुपमा चाहिँ राख्नुहुन्छ यो लिङ्क्स
सेयर गरिदियो। नलेज जति सेयर गर्न पाए त्यति नै हामीलाई चाहिँ राम्रो हुने त हो नि। नलेज चाहिँ सेयर गर्ने। ल,
सो अरू क्वेसन सर म्यामहरूको खास
राखिरहनुहुन्छ साथीहरूले थाहा पाउने बित्तिकै।
60जनाले हेरेको देख्छु मैले, त्यो हिजो राखिसकेको थिएँ। 60जनाले हेरेको छ, तर यहाँ चाहिँ 20-22 छैन।
ओके, अरू केही क्वेसन छ त सर म्यामहरूको?
अझ पनि स्टे सेफ भन्नुपर्ने अवस्था छ।
ओके, सो डेफिनेटली आजको सेसन चाहिँ अलि किनकि अलिकति हामी टिचर एजुकेसन त्यसपछि म्याथ एजुकेसनमा काम गर्ने भएको कारणले, अलि टिचर भएको कारणले चाहिँ बढी जसो अब डिस्कभरिजहरू भएको छ होइन। अब नयाँ डिस्कभरिजको लागि हामी प्रिपरेसन गराउनुपर्छ हाम्रो स्टुडेन्टहरूलाई होइन। जो सानो बच्चाहरू छन् उनीहरूको लागि पनि त्यो पार्टमा जानुपर्ने हुन्छ। अनि एज अ टिचर चाहिँ अलिकति जस्तो हामी अलिकति यो कन्टेक्चुअलाइज्ड होइन लर्निङको कुरा गरिराख्दाखेरि चाहिँ पहिला यो म्याथको जति पनि यो वन्डरफुल डिस्कभरिजहरू भएको छ तिनीहरूलाई चाहिँ कसरी लिङ्क गर्ने भन्ने पार्टमा चाहिँ होइन सरले आज अलिकति रियल वर्ल्डसँग कसरी, जस्तो गोल्डन रेसियोको कुरा चाहिँ आर्ट एन्ड डिजाइनमा कसरी चाहिँ युज भइरहेको छ होइन। अनि जस्तो त्यो फ्लावर्सहरुमा भयो अनि अरु 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 डिजाइनको पर्सपेक्टिभमा चाहिँ कसरी त्यो लिंक गर्न सकिन्छ भन्ने कुरा आउँदाखेरि चाहिँ अलिकति कनेक्ट गर्न पनि सजिलो हैन अनि त्यसलाई चाहिँ हामी क्लासरुमसम्म लान सक्यो भने अझ कहाँनिर छ त त्यसो भए त्यसको युज भन्ने कुरा चाहिँ हामीले स्टुडेन्टले देखाउन सक्छौं जस्तो लाग्छ अनि सर वर्तमान सर
हो हो
सो हजुर
नेचरसँग अथवा रियल वर्ल्डसँग चाहिँ म्याथमेटिक्सलाई लिङ्क गरिसक्यो भने इन्ट्रेस्ट जाग्छ कि मान्छेको जाग्छ कि यो त युजफुल चिज छ भन्ने
So, okay, thank you so much, Bhadra Man sir, for this very wonderful session. So, अब हामी next session चाहिँ next week को यही same time मा 5:30 मा गर्छौं. So, we kindly request all the participants to join हैन तपाईको अर्को सेसन पनि जोइन गर्नु हुन रिक्वेस्ट गर्छौं. So, with this actually this brings us to the end of the session. Sir, end गरौँ होला हैन?
हुन्छ and bye bye and bye